So before we get started, a little review of algebra here. And let's start with even functions. They are symmetrical. So if we have y equals x squared, and we're looking at the area under the curve from -3 to 3, for example, we're looking at this area and this area, and we were going to integrate this function. We can see it's the area under the curve because it's positive, and we can do double from 0 to 3. We can just do this area and double it, if it's even. So odd functions are symmetrical about the origin. And for example, so that's an example of an odd function. You can see it's odd power, not a coincidence. But what we have here, this area, or this net area is negative and this is positive. They're exactly the same, so they'll cancel out. So if this were 1, -1, and 1, the integral is going to be 0 if this is odd. So if it's even, it's double when you go half of it. So now we're going to use that whenever we can. So we're going to show this infinite set is orthogonal on the interval minus p to p. So we're going to start with these two. So we multiply the two functions. And this is an even function, and this is also from minus p to p. And since this is even, we can double it. But again, let's just remember, though, that this has to be from minus p to p. It can't be from 0 to p. It's got to be equal sides on the, it's got to be equal. So we can double from 0 to p. So this is 2. And since it's integral, we have to divide by that times p over n pi, sine of the same angle. So the product is 0. Let's use the, now let's do these two. But we do know this is odd. 1 is even. It's just really not there. So therefore, that's 0. So that gives us immediately that it's orthogonal. And now our last one is this times this. So it's the product. But we do have here odd times an even. When you multiply an odd times an even, you get odd. And this is from minus p to p, so we get 0. So we have proven the set is orthogonal, minus p to p. So here's our definition of the Fourier series. So it's the function. We can rewrite the function of any f of x. And this is the sum. So what this really is what we did before. Since we have an orthonormal set, we have our bases, this, and 1. And it's written as a linear combination. So we want to be able to find these constants. Here we are, but this is a 2. So the question is, how do we find the constants? And the answer is, we're going to use the fact that they're orthonormal. We just showed that this set is orthogonal right here. We're going to take the integral. And we'll do this a couple times. First, just integrate both sides from minus p to p, and then we'll also integrate and multiply both sides by sine of x and cosine of x. So for a naught, we just take the integral of both sides. So I'm taking that, and I'm integrating minus p to p dx. And I can integrate, and this will get distributed. So I can integrate, if I drop this, I can also distribute the integral, but I also want to let you know that we can when we have the integral and a sum, they can be swapped because it's term by term. So the integral could be on the outside and here too. Okay, so now what we need to do, you can see here we have the integral of the cosine of x, which we just showed was 0. It's orthogonal, 0. And same with this one. It's orthogonal because we dot producted it with the 1 above, and we already did that. So this is 0. And so what we have left, we can integrate this. Just a naught over 2x. Those 2's will cancel. So it looks like we can solve for a naught here. And we found our a naught. Now for a to the n. What we're going to do, then integrate. So I'm going to multiply both sides by this. And that'll get distributed. Okay, so I just multiplied every term by the cosine. And now I'm going to integrate it from minus p to pi p. Constant can go in the front. And let's look at our odd and even functions. This is odd, this is even. So this is going to be, this whole thing's going to be 0. This is 0 because the original, it's an orthogonal set, and the set was 1 and cosine of mp pi x over p. So that's 0 by definition of orthogonal. And so now we just need to work this out. And it'll equal to this, but let's work on that side. Let's really just work on this integral. So if m is equal to m, here, we get, with the half in the front, and both of those will be 0. So we get p. So that's in the case where they're equal, and if we've already shown that this is an orthogonal set, so we will get 0. So putting it together, on the left is my function times the cosine that I multiplied through by, and we get p. Oops, I'm sorry, we get a naught, a n p. So we can see we can solve for, and there we have it. I'll just box that for Anne. And it's going to be the same, very similar, b to the n. But we multiply by sine of m pi over px. And we get, and this notation, by the way, over p times the inner product. Okay, let's do an example. Well, actually, let me just write this all out, basically. So here it is, all summed up. Let's do an example. And we're going to do p is equal to pi. So by that definition, it's 1 over pi x1 x times 1 is x squared over 2 times 1 over pi. So we get 0 there. a to the n. My f is x. And again, my p is pi. Those cancel out. So we do have to use parts. Or, actually, I can continue with this, but I just noticed this is odd. This is even. Product of that is odd. Oh, so that's 0. So I'm going to stop there. I didn't have to do all that work. So let's find b to the n. Maybe we won't be so lucky here. So the definition, 1 over pi x and sine. Which that cancels. So here we really have to do parts. Because we have an odd times an odd. That's an even. Think of -1 times -1. When you plug it in, it'll come out as positive. This is a pi. So we could double it. I think I'm going to do that. So double it. U times v. Oh, we do have a negative there. So I'm going to be integrating these two. And the integral cosine of nx. I mean, there's that how the n squared came out. It's 1 over n. And this is from 0 to pi. Plug in pi, cosine of pi x. Oh, that's 0. And if you remember, cosine of pi this is -1 plus 1 minus 1. To the n power. Yeah. So going back here, we found our b of n. This was our b of n. And this was 0. This was 0. So our f of x, b of n, to the sum. Oh, that's good. This is our b of n times the sine of x. But of course, this is for p equals pi. That constant can come in front. So remember, our f of x is x. And if we want to write it out, it's -2. So it's alternating. So it's our infinite series. Turns out to be just in terms of sine. And that's it for today. Thanks.